Okay, so I'm going to be talking about weather forecast uncertainty information for everyday users. Before I do, I want to explain a little bit about who I am and where I'm coming from, because you probably won't have too many speakers today with my background. I am a psychologist, but not a therapist, not the kind of psychologist you tell your problems to. I'm a cognitive psychologist, and we study how people think and remember things. And what we're looking for in general are principles of cognition, how the mind works. And my work in particular is on how people understand and use uncertainty information. And my approach is probably different from behavioral or social scientist work that you may be familiar with. My approach is lab-based. So I simplify decision tasks. They are similar to the same kinds of decisions that people make in the real world, but I simplify them, bring them into the laboratory, and then systematically manipulate variables I think will affect them, such as how you communicate information to people, to see what the outcome is. And the research questions I've been looking at for the last 20 years or so are how to communicate weather forecast uncertainty information. But before I start, I want to review the snowstorm that Brad talked about, because it is indeed an excellent case study for this. So, and I'm going to talk in feet and Fahrenheit because I'm from the US, and I can't translate it in my head, so you, I'm sure, can. The National Weather Service predicted 2 to 3 feet of snow for New York City metropolitan area. The roadways and subways were closed down for this snowstorm. This may have been the first time that this happened. But only between 8 and 10 inches fell, and so there were all these headlines, all this media reaction about how meteorologists botched the blizzard of 2015. And as Brad said, the general situation was well understood. And these analyses in the next couple slides come from Cliff Mass' blog. These are not my analyses. A low center would develop off the southeastern United States and move northward, pulling cold air off the continent and moisture off the ocean, resulting in moderate to heavy snow west and north of the low. However, the models were mixed on the exact position of the low, and Cliff has an analysis of why some models went one way and other models went the other, and why forecasters believed in some of these models more than others. But the point is that some of them had it going close to the coast with heavy snowfall over the metropolitan area, whereas others had it further offshore, resulting in less snow over New York City. Forecasters went with a more extreme forecast, and this is the same slide that Brad showed you. And what actually happened was that the low went further offshore, and there was much less snow in the New York City area. There was a lot of uncertainty in the forecast, however, and again, this is the ensemble, although maybe it's slightly different than what Brad showed you, with snowfall over New York City on the y-axis, and here is the verification time, that line, and notice that it's between 5 and 35 inches of snow, so a whole lot of uncertainty in this forecast. But uncertainty was not included in public forecasts. We were actually able to track some down on the web, but it took a lot of work to find it. By one estimate, late January 26, there was about a 30% chance of more than 2 feet of snow on the following day. Was it wrong to take precautionary action under these circumstances? I happen to have just published a study on false alarms that had some media coverage. So a bunch of reporters called me the day afterward asking, did they make the wrong decision here? And in my estimate, they didn't. I mean, if in fact what was predicted had happened and roadways had become blocked and emergency vehicles had not been able to get through, then perhaps human life would have been in danger, and a 30% chance is enough to take precautionary action, in my opinion, under those circumstances. Should the forecast have included uncertainty information? Well, here's where the debate comes. I believe, and I'm going to make an argument today to support this, that if the forecast acknowledged uncertainty in the beginning, then people may not have regarded it as a bust when less snow fell. But the opposite argument is that uncertainty information might confuse people and they might take the whole thing less seriously. So again, my research program over the last 20 years has been directed at this question: should public forecasts include uncertainty information? And I've broken it down into sub-questions. So can people understand expressions of uncertainty? Do people make good decisions with uncertainty information? Does uncertainty information increase or decrease trust? There's actually an argument on either side of this one. And what's the best way to communicate uncertainty information? So I'm going to address each of these questions in the talk today. So beginning with, do people understand expressions of uncertainty? So when we started doing this work, there was already a lot of research that addressed the general question, suggesting that people have a lot of trouble understanding, in particular, probability. So many experts have assumed in many domains that numeric uncertainty information in particular is very difficult for the general public to digest, to understand. And so they often choose to give uncertainty as categorical or verbal expressions. So for instance, a couple years ago, I had a kind of major surgery and they told me there was a small chance of infection, blood clots, and stroke. And I personally really wanted to know what they meant by a small chance. But this is how doctors actually communicate this information to you. If you go to a financial analyst, they ask if your risk tolerance is high, medium, or low. So these are categorical expressions. A similar approach is taken by the Intergovernmental Panel on Climate Change. They ask that their contributors use this set of terms when expressing uncertainty. Each of them has a numeric definition, but they think that it would be easier for people to understand if these categorical verbal expressions were used instead of the numeric versions of them. This was something that David Budescu and colleagues looked into in a study. They gave people 4 of these categorical expressions, not all of them, they picked 4, along with the numeric definitions. So notice people got the verbal expression and then the numeric definition below it. Everyone had both pieces of information. Then participants read these terms in sentences describing the climate. So temperatures of the most extreme hot nights, and cold days are likely to have increased due to anthropogenic forcing. So these are sentences that were taken right out of the IPCC report. And then subjects were asked to translate these terms. So there's likely, translate them back into numbers. They had the numeric definitions the whole time they were doing this exercise. And here's what he found. So on the y-axis here is the mean probability estimate that participants gave, plotted over the 4 terms. And notice this first term, very unlikely, is intended to mean less than 10%. And yet people on average interpreted it as 41%. They had the numeric definitions available to them. For unlikely, 33%. On average, it was 45%. Likely, greater than 66%. On average, 58%. That's a little bit closer. Very likely, greater than 90%, 66% on average. So the interesting thing to notice about this is there's kind of a regression to the mean, where although for scientists mean to express a range between very unlikely, less than 10%, and very likely greater than 90%. People are interpreting these all around 50%, and they have the definitions available to them. This is only half the story, though, because this is the Democrats. Here's the Republicans. Systematically less. These are all terms relating to climate change, and they interpret these verbal expressions as systematically lower probabilities. So the problem is that categorical expressions of uncertainty are vague. People interpret them very differently. So this is a recent study, but people have done work like this for decades showing the same thing. There is a study, for instance, that shows that people interpret the word likely anywhere from 50 to 99%. Possible has a bimodal distribution. There are a lot of people who think it means about 5% and more people who, an equal number of people who think it means about 55%. And categorical expressions are interpreted differently depending on the context. So here's a phrase that describes the side effects of a medication, that it results in a slight chance of gastric disturbances. Or, for another group of participants, it results in a slight chance of skin cancer. The participants who got slight chance paired with gastric disturbances thought that slight chance meant significantly less probability than when it was paired with skin cancer. It's the exact same term. So this shows the effect of context on verbal categorical expressions of uncertainty. And we saw in the previous study the impact of internal context, that everything having to do with climate change is interpreted as less by Republicans than by Democrats. So my argument is that numeric expressions of uncertainty are more precise. We know this. But at the point where we started this research program, we didn't know whether people could make good use of uncertainty expressions. And again, there was a lot of previous research that was kind of discouraging, suggesting that they wouldn't be able to. But when we started this line of research, we realized that previous decision research had asked a particular question. It had asked, do people make rational decisions with uncertainty? So the comparison for these studies are between human decisions and standards of rational choice. We realized our question was slightly different. All we wanted to know was whether people make better decisions when they have uncertainty information. So the comparison here is between human decisions with uncertainty forecasts and human decisions with deterministic or single value forecasts. It's a slightly different question. And we've asked this question a number of times now. This is one of the experimental paradigms that we use to ask it. Again, it's a lab-based study. We bring participants into our lab and we ask them to do this simulated road maintenance task. They have to decide, based on a weather forecast, when to apply salt brine to the road to prevent icing. They know it has to be applied before freezing temperatures are reached. So the decision is based on a forecast for nighttime low temperature. Here's the experimental procedure. We give them a virtual monthly budget of $36,000. And actually, this virtual budget is translated at the end of the experiment into dollars, about $1 per thousand. So they're actually working for a reward. The cost of treating the roads for a single day is $1,000. They get a penalty, however, if they fail to treat the roads and the temperature falls below freezing, then their budget is decremented $6,000. Each day that they make a decision, they get a temperature forecast for that night. And then when they've made the decision, we immediately tell them what happened. We give them the observation, and if there's any deductions from their budget, we do it at that point. These are all real forecasts and real observations. We took them from Spokane and Yakima in eastern Washington. And they do this for 2 simulated months. It's 60 trials overall. And then at the end of each month, we take a trust in the forecast measure. And at the end of the experiment, they get a cash reward commensurate with their ending budget, whatever they happen to have in their budget at the end, about $1 per thousand. So here's what an individual trial looks like. So this is month 1, day 1. The forecast is expected nighttime low temperature is 35 degrees Fahrenheit. Would you like to salt the roads? Those are 2 buttons. They can push one or the other. And their current balance is in the lower left-hand corner there. So they've just started the experiment. So they've got the whole amount left. This person presses the salt button, and then we tell them that the observed temperature was 32 degrees, so it froze. So this was a good decision, and you can see they're now lower by $1,000, which was the cost to salt the roads. So I've just illustrated the deterministic condition has a single value forecast, and half of participants got that kind of forecast. The other half of participants also got the probability of freezing, so we told them there was a 20% chance, in this case, for this particular trial, that temperatures would fall below freezing. And it was this second group that did the best. So this is kind of like a contest between 2 groups. And those who had the probability of freezing made better decisions, they had larger ending budgets, and they had greater trust in the forecast. We were interested in knowing how having the probability of freezing helped. So we plotted the proportion of people salting on the y-axis over the probabilities of freezing that we used in this experiment on the x-axis. And for this graph, I've lined them up between the smallest and the largest probabilities. But of course, in the experiment, they're all mixed up together, depending on the forecast. And I've plotted the people who have the probability of freezing in this pink line, the people who had just the nighttime low temperature, the deterministic forecast in the white line. And the thing to notice about this is that those who had the probability of freezing salted more when freezing was likely and less when freezing was unlikely than did the people who just had the deterministic forecast. So it's like the people with the deterministic forecast were kind of down the middle of the road through the whole situation. But those who had the probability of freezing were better able to distinguish the two situations. They behaved differently to a greater degree. We also wanted to know what would happen if we increased forecast error. So in this case, forecast error is the difference between the single value forecast and the observation. So in this forecast, the forecast is 35 degrees, the observation is 38. And so there's a 3-degree error. And on average, for this first experiment that I just described to you, the error was about 3 degrees. It was unbiased error of 3 degrees. So in a second experiment, we increased it to 6 degrees. Again, it remains unbiased. We wanted to know what would happen if we increased the error in the forecast. And what happened was that the difference between these two groups, the people with the deterministic forecast and the people with the uncertainty forecast, increased. So people with just the deterministic forecast completely lost trust in the forecast. They salted significantly less often. And it was actually colder temperatures, so they should have been salting more often, but they just stopped doing anything at all. It was as though they knew they had bad information and they just didn't want to make a mistake. They didn't want to make an overt mistake, so they just did nothing. So distrust in the forecast led to a reluctance to act. People with uncertainty forecasts maintained trust in the forecast, they continued to salt more often, and they had better performance overall. So it was actually really important to have this probabilistic forecast in the situation in which the error in the forecast increased. So we concluded from this, and we've replicated this study many times now, that people understand numeric expressions of uncertainty. I don't mean that they have a theoretical understanding of probability or expected value or anything like that. I mean they have a working knowledge. They can use this information to better distinguish situations that do and don't require precautionary action. And this is particularly effective when paired with explicit advice. So a condition I didn't have time to tell you about is one in which we gave them the single value forecast, we gave them the probability of freezing, and we told them based on the expected value, we told them when salting was optimal. We said, okay, this is a trial on which you should salt. And this group really did the very best overall. But it's critical to include the probability of freezing. If you don't include the probability of freezing, they totally ignore the advice. If you do include the probability of freezing, then they use it to their advantage. Really interesting. So forecasts with an uncertainty estimate, we believe, are more trustworthy. And we believe that this is because, as Brad said, people know that predictions are not perfect, predictions of all kinds. So acknowledging the uncertainty in the forecast seems more honest and increases trust. This is particularly important when there's error in the forecast. The uncertainty estimate allowed people to continue to trust and use the forecast. We had another study in which we looked at false alarms in particular. And this is the one that had just come out right before the New York City snowstorm. And what we found in this, we systematically increased and decreased false alarms. And what we found in this is that having an uncertainty estimate is better than lowering the false alarm rate for compliance with warning forecasts. So what I've been talking about so far is what I refer to as a threshold probability. It's the probability for the user's threshold for action. So in this task that we had given subjects, they needed to salt the roads if they thought the temperatures were going to be 32 degrees Fahrenheit or less. We knew what their threshold was. We gave them the probability right at that threshold. It turns out this is the very best kind of information that you can give a user, is the probability at their threshold for precautionary action. But oftentimes the forecaster doesn't know what the user's threshold is. They're serving a whole bunch of different users who may have different thresholds. Some might be as low as 25 degrees. So one thing that we've looked at for this kind of situation is what we call a predictive interval. This is an example of an 80% predictive interval. It tells the user the unlikely but possible values at the 90% upper bound and the 10% lower bound for a weather parameter such as temperature, what I'm illustrating here. So we knew that this was a lot more complicated than a threshold probability, and we wanted to actually put it on a website. For a while we still have a live website, but it's not kept up very well, so I'm not going to tell you what the URL of it is. And so we knew that we would have to put some sort of explanation for what this was on the website, but we thought it would be useful to investigate it because it could serve a broad range of users. So we thought about how do we explain what this value is. So this value at the upper bound. There are two ways we could describe it, we thought. We could say it's the value for which there's a 90% chance the observed temperature will be less, or we could say it's the value for which there's a 10% chance the observed temperature will be greater. So we decided to test this, asking the question, which is the best way to describe the upper bound? And we did it in the context of a decision task again. We asked people to decide whether or not to post a freeze warning for an agricultural community, and we had a little scenario set up why this was useful information, indicating that temperatures would fall below freezing. Half of participants had this first phrase, 90% less. The other half of participants had the second phrase, 10% greater. And the thing to notice about this is that both phrases are describing what is essentially the same situation. And yet what we found was that the people who had the 90% chance less phrase found that very easy to understand. But people who had the 10% chance greater phrase found it very confusing and often misinterpreted it. So based on this study alone, we thought, well, okay, 90% chance less is the best way to express this. But just to check, we ran another study in which the task was a little bit different, but it's still an advisory, and subjects were asked to decide whether to post a high wind advisory for wind speeds greater than 20 knots. This is a small craft warning in the Pacific Northwest. They had essentially the same two phrases, but now it's about wind speed, 90% less, 10% greater. Half of participants had the first phrase. Half of participants had the second phrase. Again, this is essentially the same situation. There should be no difference in how they interpret it, and yet we found the opposite. Now the 90% chance less phrase is confusing to people. The 10% chance greater phrase is easy to understand. So this makes it look like the 10% chance greater is the best way to go on this. So what we decided was it depends on the decision. If the decision concerns temperatures less than 32 degrees, then the less than phrase is better because it matches. If the decision concerns winds greater than 20 knots, then the greater than phrase is better because it matches the decision. What we think happens when there is a mismatch is that it increases mental workload. So here's a subject in our experiment. We tell him, okay, what you're going to have to decide is whether wind speeds will exceed 20 knots. So this sets up expectations, we believe, in his mind, focusing on the range of wind speeds greater than 20 knots. He thinks, this is the important range of wind speeds. This is what I'm concerned with. If the forecast comes along and tells him about the opposite range, that's confusing. That's not what he expected to hear about. And so what we think happens is that he has to translate the less than phrase into a greater than phrase, subtracting 90% from 100% to get 10%. And all of this so that it matches his original expectations. And we think that translation process increases processing load and the opportunity for error. He forgets to subtract, or he forgets to translate less to greater. And it leads to the misunderstanding that we saw. So what we think about predictive intervals is that people can understand even these more complex versions of uncertainty information if they're expressed in a way that matches their expectations. These are both very simple phrases, the less than and greater than phrase. The only difference between, the grammar is not more complex, the words are not more complex. The only difference is that one matches user expectations and the other one doesn't. So the final thing we wanted to know about predictive intervals was whether people make better decisions when they have predictive intervals. So that's the fourth study I'm going to talk about. And again, participants were asked to decide whether to post a freeze warning. Half of participants were given a predictive interval forecast, and it's a verbal predictive interval forecast like this. We did make some attempts to use visualizations, which turned out to be disastrous. So if anybody wants to ask me about that later, I'll explain that part to you. Whereas the other half of participants got a single value forecast or a deterministic forecast. And here's what we found. These are the percent of people posting a freeze warning on the y-axis. And what I've put below here is the actual forecast. So in this first forecast on the left, the threshold, 32 degrees freezing, is within the predictive interval. Where in the second forecast on the right, 32 degrees is below the lower bound, so it's no longer inside the predictive interval. The people who have the predictive interval are the pink bars. The people who are using the deterministic forecast have the white bars. And what we found was that when the threshold value was within the predictive interval, people were more likely to post a freeze warning when they had the predictive interval. So it helped them to be more active. Whereas when the threshold value was below the predictive interval, very few people posted a freeze warning, and there wasn't a difference between the two groups. So with respect to predictive intervals, we think that people can understand even this more complex version of numeric uncertainty information. And again, I don't mean they have a theoretical understanding of it. I mean they have a working or a practical knowledge. They can use it to better distinguish situations that require precautionary action. This is a finding that has now been replicated many times with a wide range of users, people with high school education or less, college education or advanced degree, young people, old people, men and women, and we find essentially the same thing. So I'm going to return now to the questions I started with. Should public forecasts include uncertainty information? And the first question I asked was, can people understand expressions of uncertainty? My answer to this is yes. We've shown it with threshold probabilities, predictive intervals, even odds ratios. So we find that for events, very rare, low likelihood events with very destructive outcomes, that odds ratios are often a good way to go. So this tells the user today's odds over climatological odds. And without any kind of explanation, people can understand and use this information. And again, my argument is not that they make rational choices or that they understand probability theory. They just do better than if they don't have that information. Do people make good decisions with uncertainty information? Yes. My answer to this is yes. They do not make perfectly rational decisions. So if we'd taken the approach of the previous research and asked, do people make decision errors? We would have said, sure, people make decision errors. They just do a better job of making decisions when they have the information than when they don't. Does uncertainty information increase trust? Yes, this is really important. And this is because people know that forecasts involve uncertainty. So forecasts that acknowledge the uncertainty seem less wrong when the single value forecast fails to verify. We've shown that it counteracts the effect of false alarms, and it increases the compliance with warnings. What's the best way to communicate uncertainty information? We believe that numeric expressions rather than categorical verbal phrases are best. And we think it's extremely important to include the information that can be used directly for the decision at hand. If you are able to do this, if you know how your decision maker is going to use this information, give them that information that doesn't require them to make all sorts of transformations where they could make errors. And an explanation that matches their expectations. So back to the New York City snowstorm. I think that if the forecast had included an estimate of uncertainty, then people would have made better decisions. They know that forecasts include uncertainty. They would still be able to make good decisions, and they wouldn't have considered a bust when only 8 inches fell. People would have understood from the beginning that it was intended as probabilistic. And so this is a list of papers that I've cited in this talk. If anybody wants this, I can send it to you. And that's all I have to say.